Ever come across a math sequence that's, well, super simple in its rule, but just goes completely wild, grows faster than you can really picture, and then reveals this hidden link to something continuous? Welcome back to the deep dive. We're here to pull out the key bits of knowledge, fast and hopefully fun. Today, especially for you number theory students listening in, we're diving into a really neat corner of the OEIS, that's the Online Encyclopedia of Integer Sequences. We're looking at sequence A000283. It's known as the sum of squares recurrence. Okay, let's unpack this. So the basic idea, the definition, it's actually wonderfully simple. You get the next term, an, by squaring the previous one, an1, and adding the square of the one before that, an2. So an1, 2 plus an2, 2. That's 4n bigger than or equal to 2. And it all kicks off with a0, ai1, s1. Pretty basic starting point. All right, let's see how it plays out. You start 0.1, okay, then 1 again, then 2.529. Then 866, still kind of manageable, right? But hold on. The next term is 750,797. And right after that, we're talking 563 billion. I mean, that's not just growth. That's like an explosion from almost nothing. What's going on here? What kind of mathematical fireworks are these from such, well, humble beginnings?
It really is something, isn't it? That squaring operation is the key. It just amplifies the term so incredibly fast, it really pushes the limit of how quickly a sequence can shoot up. And, the OEIS tags this one non-negative. Seems obvious with squares, maybe, but it's an important thing in the number theory. Some sequences dip into negatives, but this one just keeps climbing.
Okay, so just when you think you've got a handle on this discrete integer sequence thing, this crazy growth, there's another layer. Turns out there's a kind of continuous approximation for it. For n that's 1 or more, you can actually estimate an using this floor formula. It's an floor, a to n1. Now, floor just means, round down to the closest whole number. And this a, it's this very specific constant, about 1.23539. And it just goes on and on.
Right, and that constant a, that's where things get really profound, especially for number theory students. It's not just some random number that happens to work. It suggests a deeper structure connecting the discrete world of integers with the continuous world, like a continuous shadow cast by this integer sequence. It really makes you think, doesn't it, how these different mathematical areas can link up in unexpected ways.
Interesting. So simple rule, crazy growth, and now this connection to a continuous formula via A. Does it pop up anywhere else in practical applications or other theories? I think I read something about Benford's law.
Ah, yes, Benford's law, absolutely. Benford's law looks at how often digits like 1 or 9 show up as the first digit in big sets of numbers. And sequences like this one, A000283, because they grow so incredibly fast, their terms spread out over many, many orders of magnitude very quickly. And yeah, they often turn out to be good examples for Benford's law. The leading digits tend to follow that specific logarithmic pattern the law predicts. So you see more 1s and 2s than 8s and 9s as the first digit. It makes A000283 a really useful case study, like Stephen Miller mentions in his book on Benford's law.
Got it. So it's not just a theoretical curiosity and for anyone doing computational work.
Oh, definitely. Handling these huge numbers, going from 866 to billions in 2 steps, that's a computational challenge. It's actually a great sequence to test how well you can handle large number arithmetic efficiently. People have implemented it in tools like Maple, Mathematica, Perec, Maxama, so you can play around with it.
Right. So wrapping this up then, OEIS A000283. It's kind of got this dual personality, hasn't it? Simple recursive rule leading to this mind-blowing growth, but then also this surprisingly precise continuous formula involving that constant a. We really do encourage you, if you're interested, go explore the OEIS. It's just a treasure trove.
Absolutely. And maybe a final thought to leave you with. Think about how sequences like this one start so simply, just 0 and 1 and adding squares, but then they explode in ways that feel almost unpredictable. It sort of challenges our intuition about patterns in math, doesn't it? What does predictability even mean when things grow this fast? What other questions does that kind of rapid expansion bring up for you?
Definitely something to ponder. Thanks for joining us on this deep dive. We'll catch you on the next one.